So today we will start on this exciting journey of retracing one of the romantic moments of physics. This is Niels Bohr model for the hydrogen atom. So the lead up to this piece of work is quite interesting. In the 1840s onwards, people had studied the light coming from different sources, and they had discovered a link between the environment through which the light went and the missing of certain spectral lines. And one of the great innovators was Fraunhofer. Fraunhofer was someone who was extremely poor, and he got into a glass polishing company. He was working there, and there was an accident and the whole building collapsed. He was buried underneath the building. So after many hours, he was pulled out and he was alive. And so the rich person there, the king or whoever he was, he gave him a large sum of money because he had survived. And using that, Fraunhofer started his own company, and besides making glasses and prisms of very high quality, he started very systematically studying spectral lines, the lines emitted by different atoms. And what was revealed was that the light which was coming out from atoms had some sharpness. There were discrete lines. And the problem was, could one understand how they came about? So this study was called spectroscopy. And very soon people had this vision that by looking at the spectrum, you might be able to identify the constituent of a star. The French philosopher Comte had said that science will never be able to find out things about stars because you have to be physically present in order to carry out experiments. And it is quite surprising that that kind of robust argument was shown to be wrong. So this is one of the lessons one learns, that if you are a great expert, then very often you're likely to be completely wrong outside your own time frame and outside your own speciality. There's so many beautiful examples of this. So coming back to these spectral lines, there were people who suggested that maybe there are some oscillations happening. People knew that there was a charge. J.J. Thomson had found that there were charges, negative charge, electrons were present, and there was a positive charge had to be there because the thing was neutral. And there were various models, the jelly model, the jellynium model, or whatever. And the idea was somehow these things were oscillating, and the oscillation, according to Maxwell, if you have something which is accelerating, it should emit radiation, and maybe one should try and explain what is observed on that kind of microscopic basis. Now, if I do an order of magnitude calculation, the kind of things I was doing a bit earlier, then you would say atom has some characteristic length d, and so there will be a characteristic wavelength lambda, which should be related to d, and so lambda into omega is some canonical speed. And if we look at something which is of one dimension, just to get an idea, one-dimensional oscillation like this, then the lambda will be like this, lambda 0, then you have lambda 1, the different modes. And what you find is that lambda n is related to d over n. So whatever your length is, these are shorter like that. So that would mean then that lambda n, omega n is equal to c for this wavelength, and so omega n into d over n is equal to c, and omega n should be c over d into n. That's a prediction. Sadly, the prediction didn't seem to match what was experimentally observed. Then a breakthrough happened in 1885 when Balmer, who was a school teacher, he was just looking at ways of fitting data. He had no theory, nothing like that. So on the basis of that, in modern day language, he found omega nm. He didn't really do all of this. He found the one where n was 2 and m went on from there. So you had a surprisingly easy looking formula, but it was surprisingly different from this. So something had to happen, some new idea had to be introduced. And this whole process there's a book by Whittaker on the history of ether and electricity. And there he goes through the history of what people were trying to do and what people found slowly. So leaving out all of the history, we come to the way in which Bohr suddenly emerged and suggested something quite unusual. So before we do that, we should remember that at that time, Rutherford had made a model in which the proton was the center and you had the electron outside there, and this radius was r, and the mass of the electron was known, and this was going with some velocity v, and this was established. And so for this system, you had energy which was half mv squared minus E squared over R. So this is the energy. This was known. Unfortunately, this picture could be immediately ruled out using the ideas of Isaac Newton and James Clerk Maxwell. So the two outstanding classical theories said this was completely wrong. Why? First, Newton and then Maxwell. So Newton said that if something accelerates, if it moves in a circle, there is acceleration. This we have just used. Maxwell said if charge accelerates, it loses energy, radiates. So as it radiates energy, that means that this E becomes smaller, and E becomes smaller, that means that R becomes smaller. And so at the end, the stable configuration is when this charge and this charge are sitting together on top of each other. But the size of atoms observed was not the size of the proton, but of the order of a couple of angstroms, 10 to the power minus 8 centimeters. Right? So these two things ruled this out, and so Bohr had to, he was completely aware of all of this, and he had to find some way in which he could approach the problem. So what he did was, he first said, I must tackle the problem of losing energy. That is the stumbling block. If you lose energy, you're finished. It will collapse. So he said there are special orbits where the system cannot lose energy. He said, why do you know that? He said, because I say so. Very convincing argument. This is a way of argument which is by assertion. And so he asserted that the special orbits where no radiation loss takes place. Okay, so but he just didn't leave it there. He characterized these things. He said they have to have a special property, and so these special orbits were the ones where m into v into r was n h bar. H bar is the Planck's constant of r times. H bar, the old Planck constant divided by 2 pi. Okay, so that was now he's fixed those. The second thing he said was that the classical laws still work. Although he has thrown away Maxwell and thrown away Newton, but he said, I'm not quite going to throw away Newton. I will assume the energy which these great people have suggested still valid. So the energy is still half mv squared minus e squared, and still you have m into v squared over r is equal to e squared over r squared. Hold. Right. So that's the thing. But now that he stopped radiation and said this, where does the light come from? So he made his third statement. The light comes due to a transition. So these are special between special states. And the omega nm is equal to En minus Em over h bar. You see, this thing is some way reflected the omega nm of r into 1 upon n squared, 1 upon m squared. This is Balmer plus. Okay, so this thing, if you know the formula out there, right, then it seems that if I have the difference of two terms, this will do it. You have two terms and you have a transition, and that will work. Okay. The question, theoretical question is, where do the photons come from? They cannot come from these because there is no radiation from them. Each one cannot radiate, right? So there is no photon, but the photon appears. All of this Bohr knew. It's not that he did not know. He knew very well, right? But he said, let us see what this leads us to. Okay? And what he did was then show from these assumptions, one could actually calculate the value of R. And he could then start on this road towards understanding spectra. Originally, chemists did not pay any attention to Bohr. They had their own orbital and other pictures, and they were very comfortable with them. And slowly, it took quite some time before the community of chemists came on board, right? But you can understand their misgiving, because they would say this is typical theoretical physics people who live in their own world. In those days, there was no 26 or 10, but there were normal 3 plus 1 dimensional space. But even that thing, they make up their own rules, they make up their own things, and we don't pay any attention unless we have to, if there's some advantage. Okay, so let us work out the consequences. So to work out the consequences is straightforward. And with Niels Bohr, whenever he met his students or anyone, he would go over his struggles to get this point before he looked at any other problem. So there was this ritual that you had to sit and listen to him go through the whole business, and then you would start on your own thing. He was getting his mind ready to look at new ideas. So how to proceed? Well, first step is this stationary condition. If I square this, then I get m squared v squared r squared is n squared h bar squared. Right. So we find that m v squared r squared, m v squared is equal to n squared h bar squared over m into 1 upon r squared. Right. So this is one equation. The second equation was, from this equation we find that E is half mv squared minus e squared over r, but mv squared, so this is half mv squared is e squared over r minus e squared over r, which is equal to minus half e squared over r. So what we have are these two conditions, and so what we have to do then is write down, right, this thing from this expression is equal to mv squared is half e squared over r, right, mv squared is half e squared over r from this equation of motion. So what we find is that 1 upon r is m e squared over n squared h bar squared, and and there's a half. Okay, so once we have this, then you immediately find from here this is equal to minus half m e to the fourth over n squared h bar squared, and there's another half in my particular thing, but there's half r, right? So in my thing, I'm not too worried about factors because everyone knows these results. This is just symbolically what are the inputs which give rise to the result. So what we find then is you have expression for En, which is completely fixed by the numerical constants of physics. The mass of the electron is known, the charge of the electron is known, n is an integer, h bar is known. So that means that in this formula, the r which is there is related to m e to the fourth over n squared h bar squared. And in my thing, this factor should be half somewhere. I've not paid too much attention to it, but there you have it. Okay. Oh no, there's no half here. Right, sorry, that was a, yeah. So this is half. Yeah. So yeah.
R doesn't contain the ends.
Yeah. R does not. No, but here, this is okay. This is so R does not contain M. Yes.
Yeah. R is just a constant. So
Yeah.
you don't have an ends there.
Yes. Yes. Okay. So, but this is the result at the end. Right. Okay. So, what you find then is an expression in which you have explicit formula which gives you a result. The disadvantages of the formula I have stressed, that they do not actually give you some insight into what is going on. And all of these problems were sorted out fairly soon when the quantum mechanics revolution happened. So what I want to do now is to start talking a little bit about that revolution. So I'll talk about the thing in a roundabout way. Tomorrow I will talk about that in greater detail. But today what I will say is go backwards a little bit, and I would say that in the kind of physical world in which Bohr grew up, in which Einstein grew up, where at the background there was the laws of Newton, the laws of Maxwell, there was determinism. People knew that if you're given the initial conditions, then everything could be predicted. So if you launched a satellite, if you wanted the satellite to go in a certain orbit, you could choose the velocity with which it is launched and you will get that orbit. But Bohr was saying this is not possible. That no matter what your initial condition, the stationary states were independent of initial condition. This was a very different picture. So it was completely contrary to the insights which physics people had built up over many, many, many years. The second thing was that, as we will see, that this introduced, on the one hand, this certainty that there will be certain stationary orbits, but at the same time, when quantum mechanics came about, it replaced classical determinism with uncertainty at the microscopic level. So before, there was a notion of probability, but the notion of probability was for complicated macroscopic systems, which was due to the fact that you didn't know enough. So I will briefly talk about this because I will need the concept of temperature in subsequent places. So let me discuss that, and then I'll come back to this. You see, if you look at a collection of n molecules, right, and these molecules, we suppose they are all free molecules, and so each one has half mv squared kinetic energy. So they're moving around. So this has some energy. For the moment, if it's got potential, it won't change the argument, right? So n in one cubic thing is 20 molecules in a mole. Right? A very large number. So if you know each and every position and momentum of all of these molecules, it is useless, because the subsequent evolution cannot be tracked. There will be collisions and it's just impossible. So people said that maybe we can look at a notion that the whole system has energy E. The whole collection has energy E, and this energy E, there's a probability for the energy. So from what we know from physics, the energy is something which is conserved. It's fixed. There's one value for energy. Even though it's a complicated system, the energy at the initial part has some value and is fixed at that value. So what is the talk of probability? Okay? Because it's a fixed value. Right? So the idea was that, although that is true, but let us allow the thing to vary, and what we were saying is that the energy will settle down near some value which is the fixed value. So in other words, you are throwing away one part of physics. You're saying that in this probability approach, we will throw away a certain part of the physics. Okay, and once you do that, then if you require that P plus E0, P of E2 plus E0 is equal to P of E1 over E2. So this is the probability you want to find. You say the scale doesn't matter. The energy scale, I can choose to be E1 or E2. I can shift them both by E0, and this will not change. If you do that, then the solution of this is P of E is equal to C e to the power of minus beta E, where beta is a parameter which has the dimensions of 1 upon energy. This is the solution of this. This is not, so the assumption is it's a continuous range of E. Okay? So once you've done that, then you say that P of E, sum over all E, has to be equal to 1. And so that means that if I sum this, I get, which means that C summation e to the power minus beta E is equal to 1. And so you find that this quantity, summation, call that defined, right? Sum over E. And so what you find, this C is 1 upon Z. And this will be called the partition function. So from a very simple starting point, what you find is P of E is equal to 1 upon Z okay. So now beta, we don't know what it is. Okay. So beta, we don't know what it is. So what we want to say is that I have to make an identification. I have to put in some physics. So the identification made is that if I look at the average value of the energy in this system, so the average energy is this, and you identify this with the internal energy of that system. Identify. Now, this object which we have here, I can write as dd beta with a minus sign of Z. Right? So if I take Z, 1 by Z. So I take this quantity, differentiate with respect to beta, I pull down a thing, right? I differentiate with respect to beta, I pull down the thing, I pull down E with a minus sign, pull down E with a minus sign, so this quantity is equal to U. So this means that dd beta of log of Z is U. Then from thermodynamics, which I will not go into, there is a formula which tells you that U is equal to dd 1 upon kT of F over kT, where F is a free energy. Right. So that means that we can identify this log thing with F over, so identify there's a minus sign, and beta so I went through this sketch, right? I've written a book on StatMech where I use this. Okay, so I do much more, but this is a thing to show that very often if you stick to and the original, this argument is due to Feynman. Feynman's book on statistical mechanics uses that argument. Okay, so I found that there are many arguments. I'm not saying this is better or worse, but it seems to me it is a royal road. That is, you are not messing, you're going straight to the point. And this derivation is rather easy. You just make a delta E and differentiate, and you get that result. So it's not a complicated calculation. So the whole point is that this thing shows that the KT part is related to energy and is related to the average energy of a system. And this is something for an n-body system, it is nkt, will be the kinetic energy, the rough kinetic energy. This quantity, when you work this thing out, is related to nkt for a free particle. And this is something which I will use later on. So all of the thermodynamics which is necessary will take too long. I will not go into this. The idea of what is F is the free energy, and U is the internal energy. All of these concepts are concepts which take long time to explain, and so I'm not going to explain them. But all I wanted to point out was that even for a complicated system, you can try and approach the complicated system by using very simple principles. But once you made the simple principles, you have to make an identification. And the identification is where all the learned people have an advantage, because the learned people know these kind of relationships, right? And they know what F and U, all of these things mean. But if you don't know, don't worry. All I'm saying is that there's identification, and once you've made the identification, all you need to know is that Z is e to the power of minus beta F is equal to summation over E to the power minus beta E, and when beta is 1 upon kT. And the learned people in thermodynamics will tell you that if you know F, you know all the thermal properties of the system. You can do various things, and you have all the properties. You can work out the perfect gas law. All of those things will come out from F once you've known it. And what is E for a system? It will be P squared over twice M, or half mv squared, and you're integrating or doing whatever you want, right? So this notion of probability was well established in physics, and people had accepted it and had started using it very successfully. However, in the quantum world, it was not this kind of probability. It was probability at the level of each atom. Each particle had an inherent uncertainty, an inherent lack of clarity. Inherently, the system was not deterministic. That whenever you're making a prediction, you could only talk about probabilities. You could never say this will happen with certainty. And this was again a huge revolution in physics, which we are still struggling with it. And more insights into the miraculous nature of the quantum world are emerging, and more tests which study the extravagant predictions made in quantum theory about long-range correlations and entanglement. All of these things are slowly getting experimentally established. So it's an exciting world where all of these things are happening, and part of it is due to more theoretical tools, and part of it is due to the exquisite experimental things that are happening. The kind of things which you can do nowadays, you cannot dream about them 10-15 years ago. It is just absurdly beautiful. Yeah. And so that is the world into which the younger people now are walking in. And the British philosopher said that the point of education is to train young people for the adventure of life. And that should be remembered. One other little point I would like to make, which is the general theme of these lectures has been to emphasize simple ideas, but each time in the simple idea, I've always said it only works if you take the infinite limit. If you does this only for infinity, so the infinite thing happens constantly. So in one of the Indian learned books, they had this beautiful little statements. They said, where there's creation, there's progress. Where there's no creation, there's no progress. Know the nature of creation. Where there's joy, there's creation. Where there's no joy, there's no creation. Know the nature of joy. Where there's infinite, there is joy. There's no joy in the finite. So that is, I think, a good time to stop today.
Thank you.